Okay, so our first lab is a measurements lab, as you can tell by the title of the lab, and it comes in basically 4 parts, or maybe 3.5 parts. Anyway, the first part is to measure carefully as possible, using a meter stick, the 3 dimensions of a 2x4. Now, I've cut these off so that unlike 2x4s, they don't have a rounded edge, so we don't have a problem with what's called a problem of definition. That is, where is the edge exactly? It's pretty clear. So, assuming these are all squared off, that may be a bad assumption, but assuming that, we need to measure with the meter stick the 3 different dimensions, and then, as we talked about last week, processing those values and the uncertainty in those values, which is the maximum deviation, because we're only going to measure it 4 times, I think, in each dimension, to get an average and get a maximum deviation. And we're going to process the data as we talked about, as it's kind of laid out on that tear-off page table that you have with this lab right up. So let's take a look at this. First of all, this is my 1.004 meter stick. So we don't ever use the ends because, first of all, they're not 0, but you never use the end anyway because you don't know if it's worn off. So never use the end of the meter stick if you can avoid it. And we're just going to, we don't necessarily, we should not assume that this scale is uniform throughout, although it probably is, but we don't want to measure in the same location 4 or 5 times. So we're going to measure this, move it down the meter stick, and down the meter stick, and down the meter stick, as many times as I have blanks in that table for you to record the length. And of course, measuring the length, another thing that you don't want to do is set this at, say, 10 centimeters, and then measure this as 24.8 centimeters, something like that. That's not going to be accurate because you've made an assumption that this is at exactly 10, and then you've read that. So you haven't treated those 2 ends equally, and you can't do an error analysis on things that aren't treated equally. When you subtract them, you're going to have a problem with what is the error. So just plop this thing down arbitrarily, any old place along the meter stick, and read the 2 ends and subtract the 2 ends. Of course, that doubles the error, as you know from last week's discussion. There's an error in each one, times 2. And so we just read it. This end reads 17.05, and this end reads 6.54. What I'm doing is, and we'll show you a close-up in a minute, what I'm doing is I'm interpolating in between these marks. There's 1,000 marks on this meter stick, there's 1,000 millimeters in the meter, and I'm interpolating in between those marks, making an educated guess as to whether it's a quarter away over, halfway over, 3/4 of the way over. If you really want to get good, you can estimate it to the tenths. So it's 3/10 of the way over, 6/10 of the way over. Of course, that last number, because that last number always is got some error to it, and any significant number, that's fine. It could be off by 0.1 or 0.2, but it's not going to be off by 1 whole millimeter, or probably not even a 1/2 millimeter. So you get some information in that last significant figure. The last significant figure has built-in uncertainty. And it should have built-in uncertainty because that means you've taken the instrument and you've read it as carefully as you can, and the last number you're not quite sure about, but you're going to take a good guess at it. And that's called the last significant figure. Okay, so then you subtract the right value from the left value, and that gives you the length. If you do it backwards, you get a minus sign, discard that. So measure this length, width, and height, and then process the data in that table as we talked about last week. Okay, so here's the left side of this, a close-up by the meter stick, and let's take a look at the end. Let me get this a little bit brighter here. on the end. Okay, so what would you read that as? I would get 24, just look at the bottom end of that, as it touches the meter stick there, 24.75-ish. And that's the last significant figure is kind of fuzzy. You might argue it's 0.7, you might argue it's 0.4. I'm going to say it's 0.5. So we would all be right because that's the best we can read that. So 24.75 is the reading on that end. So we want to measure also the volume, length, width, and height of this using a more accurate, we hope, instrument, which is the caliper. And again, you've got the handout, and you have a photo of the caliper, and kind of an explanation of how it works, but I want to go through that again quickly. So here's a vernier scale. Now, the index mark is this mark right here, and the mark right above it. This scale and your caliper, the sliding scale is on top here, but the sliding scale and your caliper is underneath. So this is kind of upside down. So this is actually your index mark on the sliding scale. Wherever that mark is, that is the reading, that is the length that you're going to measure with the caliper. So you'll notice that the scale here has 10 divisions, and the scale down here, which is the actual millimeter scale, this is a simulation of the millimeter scale, has also 10 divisions. But this 10 here is kind of hovering over the 9 mark. What that means is these spacings here are basically 9/10 of the spacings over at the bottom here. Now that sounds a little confusing, but Mr. Vernier, who was a 18th century Frenchman, was very clever in this, and he realized that as you go down the scale here, let's just put this at some value, at 5 centimeters. Okay, so at 5, well, I'm going to call these centimeters. So at 5 centimeters, this is lined up. The index mark here is lined up, and the line that lines up best is this line. Of course, I lined it up that way, and the line that lines up best over here is the 10 mark. Each one of these lines, you notice, let me move this over halfway. Okay, so this is going to be 5.5 centimeters, as I would read a meter stick, for instance. But because each of these spacings is 10% smaller than these spacings down here, the next spacing is going to be closer to the mark below it, and closer and closer. And so if you look over here, these two lines, this line and this line, are lined up best above and below each other. And so what that means is this is 5. Not 5. You probably look at this a little more carefully and see it's a little bit below 5. It's a little bit below half between this number, 5 and 6. And so what that means is it's pretty clear that these two lines line up best with each other out of all the lines on the scale. And so that's because each one of these lines is closer. So the fourth line is 4/10 closer, meaning that this is 3/10 closer, this is 2/10 closer, this is 1/10 closer, and that's right on the money. So Vernier discovered you can get another honest, significant figure out of this scale using his Vernier scale. So the line that lines up best is the fourth line. So this reading is, you don't have to guess, it's 5.4. So this caliper is a little more accurate than the scale that we have here. It's accurate too, according to the very fine writing on the sliding scale. Again, the index mark is at the 0 of the sliding scale. It says 0.02 millimeters, which means it's theoretically accurate to not a tenth of a meter, but 0.02 millimeters, which is 5 times more accurate than even if you could guess, even if you didn't have to guess on a meter stick. So it's like 20 times theoretically more accurate than reading and estimating that last digit on the meter stick. So let me put this block in, and this is the way you do it. This has got a little thumb adjuster here, and if you, when you let up on it, it kind of locks that in position. When you push into it, it allows this to move. And so one can let up on it and take it off and read it, but if you do that, it's pretty clear that that your reading is going to be a little bit on the high side. Since this can measure to 0.02 of a millimeter, you want to keep tension on that and read it while it's got it's under tension. So I'm going to read this, and I can't show you this because it's too fine and too far away, but this reading is going to be, I'm reading from the index mark. So the index mark is between 3.6 and 3.7, really close to 3.7, but below it, centimeters. Okay, 3.6 something centimeters. And so to find that something, you look up and down the scale here, and the scale on this caliper has 5 times more markings than the scale on this caliper, making it a little more accurate. And so you look up and down the scale, and you find it's got 50 marks. Each one of those marks is actually 0.02 millimeters. And so you can read to the nearest 0.02 millimeters by lining up the marks. As we saw over here, the mark that lines up best, that's the mark you're looking for. So I'm looking for that mark, so it's 3.6 something, and it's pretty close to 3.7, so I'm going to look towards the end, the high end of the scale, and it seems to me that the first mark past 8 is the mark that lines up best with the mark above it, so that would be 3.682. Each one of those little marks on the scale is actually 0.02 millimeters, and that's how accurate it is. So, or potentially accurate it is. So 3.682 is the reading. And I read that with it under tension. And you can read anything up to 6 centimeters in any dimension to the nearest 0.02 millimeters. The second part of the lab is really pretty simple and pretty quick, unlike the first part, which involves doing experiments 5 times each dimension with the meter stick and 5 more times each time with each dimension with the caliper and processing today. So that's actually way over half your lab. So part 2 is to calculate the density of wood. And as I mentioned in the write-up, most wood floats, therefore we know the density of most wood is going to be less than the density of water, which is 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter, whichever. So you're expecting a number less than 1,000. Again, everything should be in this calculation should be in MKS system, that is not centimeters, not millimeters, but meters, and not grams, but kilograms. So kilograms per cubic meter. That's a big number. 1,000 kilograms per cubic meter is literally a ton of water, but a cubic meter is a lot of water too. So, in any case, so this is a double pan balance. It's according to its manufacturers. It's accurate to 0.01 grams. That's 0.01 grams, and it can measure things up to 210 grams. This fortunately has a mass of a little bit less than that. So the first thing you want to do, and I should turn this more to the camera so there's no parallax. If you look at the pointer and the scale here, it's set at exactly 0. If it isn't set at exactly 0, there's this knob here which you turn like a tenth of a turn, one way or the other, depending on, you'll have to figure out which way to turn it to make it balance the right way. So I would turn this by a little bit, a tenth of a turn if it's really close to balance like this is, and then see if it's closer to that 0 mark or not, and keep doing that until it's on the 0 mark. This is, of course, a systematic error, which we want to eliminate, and we can eliminate by making 0 really 0. Okay. So I'll put the block over on here, and there's this is a double scale here. I'm going to run this up until 160 is not enough, and 170 is too much. So I'll back it up to 160. This is by 10 grams. Then this top scale is all the way from one side to the other, 10 grams. So I'm going to scooch this up until it kind of helps to have something smaller than your thumb to do this with. But I'm going to scooch this up until, once again, the scale is balanced. And I think I accidentally, but the last little scooch got it balanced. So the reading is 166 grams, and I get the next decimal point here, and it looks like it's just a little under the 9 mark. So I would call it 166.89 grams if you really want to push it to the nearest 100th of a gram, which theoretically you can measure it to if you, again, like you did with a meter stick, interpolate in between these lines. It's just barely under the 9 mark, and so I'm going to call it 89. So 166.89 grams. Convert that to kilograms, that'd be 0.16689 kilograms, and divide that by the volume that you calculated in part 1 in cubic meters. And see what you get. Hopefully it'll be less than 1,000. Okay, the third part of the lab is to quickly get quick and dirty data, which you don't usually want. I usually don't want you to get, but we want 10 numbers to take the average of those numbers and do a standard deviation calculation. So we want some 10 numbers that are supposed to be the same number quick. And so we will do this, and you may have already calculated that it takes about 0.4 seconds for an object to fall 1 meter. So, and you should calculate, there's a formula in the write-up, lab write-up, to give you, if we haven't gotten to the linear motion discussions yet, to calculate the time it takes for a freely falling object, a ball bearing, to fall 1 meter. Now, this is a 1.004 meter stick, but this is a crude experiment, so we're not going to worry about the 0.004 because it's totally trivial in comparison to 10 or 20 or 30% error that you're going to get because this is a really crude experiment. So we're going to drop this ball 1 meter and time it. I don't have a partner, so the partner, somehow you and your partner have to decide how to do this, whether you do all the timing and the looking, or your partner calls it and you just do the dropping. You have to figure that out, and part of the lab report is to tell me how you actually did the lab, so that I can see where the errors might have come in that procedure. So in any case, of course we drop the ball. Where do you drop the ball from? What actually falls 1 meter when you drop something? Well, it's the bottom of that something. So you want to start with the bottom of the ball at 1 meter and let go and do the timing. Again, how you coordinate this timing is the real big deal. I've seen some results that have been amazingly accurate, and I've seen some results that have been all over the place because of the technique or that the people have decided upon. So you might want to try this several times before you decide on an actual technique, so that if you get consistent results, even if they're consistently wrong, at least you get consistent results. So I'm going to drop this, and you can borrow one of our stopwatches, or you can use your stopwatch feature on your smartphone, whatever you're more comfortable with. So it may take some practice to start and stop that accurately in less than 1 second between start and stop. So play with that. So anyway, however you decide to do this, drop the bottom of the ball at 1 meter and start and stop the timer. That's it. So before I go on to the next part, I'd like to tell you a little story about vernier calipers. It's important for you to get to learn how to use these things. You just never know when you're going to need this kind of information. Several years ago, actually not too many years ago, one of my alums came back and said that he got a job at an engineering firm with 100-some engineers. And they one day had to measure the diameter of something that was fairly large, and they had digital calipers that just give you the answer, but they weren't big enough to measure that. And they looked all around the shop and the factory, and they finally found a caliper that was big enough to measure that, but it was a manual caliper. So they asked around if anybody knew how to read a caliper, not just look at what the number says on the dial. And the only person in the whole factory of the 100 engineers that knew how to read a caliper, because he learned to do it in physics class, was one of our alums, and he saved the day. So reading a caliper, when your batteries run out, or you're on a desert island and you only have a caliper, you know how to use it. So the last part of the lab is to do what we briefly talked about. Remember, we plotted a slope of one straight line and showed you how to get the sloping intercept and the uncertainty in the sloping intercept off of graphical analysis. So we're going to do that here for real. This is the formula that relates the length of a pendulum to its period. And I'm going to rewrite it this way because I want to show how it compares to the slope-intercept, y-intercept form of a straight line. Again, this is not a straight line, but if we do, as I said before, if we have a curve, it's very hard to see whether your data points fit the ideal curve or not, because we're not used to comparing things to curve. But comparing things to straight lines is pretty straightforward, you might say. So if we plot this period of the pendulum versus length, we will, and the square root of the length, we will linearize, so to speak, or make it look like a linear relationship. The relationship that this should obey is the period and is related to the square root of the length. And the relationships here are what's out in front of the length is 2 pi over the square root of g. You know what g is, 9.8 meters per second squared. And so this is a number that's easy to calculate, and you should calculate it because you want to see if your slope comes out to be that value. And L to the 1/2 is the x-axis. And so the slope is 2 pi over the square root of g, and the x-axis is the square root of the length. And the y-intercept, of course, theoretically should be 0. A zero-length pendulum has no period. So we've converted it to looking something like the slope-intercept form of a straight line. These are the numbers you should be getting. And so we will get, again, if you push the analysis box, you'll get the slope, the intercept, and the correlation coefficient, which should be, since we've linearized this, really close to 1. It should be 0.99 something, really. And then if you double click on this box, you'll get the uncertainty in the slope and the intercept. And of course, your slope should be, your experimental slope should be this number, whatever it is, give or take. Your experimental value should be, should contain the range here, should contain the actual slope value, which is, depending on the units used, I would recommend meters and kilograms again, within that range. So if your data include the value that's within the range this is within the range, and you've got some good results. And of course, B should be really close to 0, because theoretically it should be 0. So discuss these results. Hopefully your value will include this value in its range of uncertainty. Part 4 of the experiment is to time the length of a pendulum. We just talked about the theory behind it. Measure the length of the pendulum and measure the time it takes to go through one complete cycle, which is starting here, back here. Or if you start in the middle, it has to go through the middle in the same direction. So one complete back and forth cycle, however you decide to time that. And that's up to you to practice and figure out how to do that best. So, the world is not made of experiments like we're doing in the lab. You might wonder why we're doing these things, because if you get a job as an engineer, for instance, they're not going to pay you to measure the coefficient of friction of something sliding down an inclined plane. But that information is transferable to much more complicated situations, and you need to know the basics, which is what we're doing in the lab here. So in the labs, we try to set these things up so that we focus your attention on the things that are important that we're studying, and don't worry about or minimize, downplay everything else. So we're wanting to study a simple pendulum, and you might say, well, this is about as simple as you get. It's a light piece of string, one of these massless physics strings that we use, with something on the bottom called a bob. These bobs are, by the way, I'll give you this gratis, these bobs have a 1-inch diameter. So you can convert that to centimeters, and you'll see that we need to use that in a minute. Okay, so this is, as I say, about as simple a pendulum as you can come up with, a more or less massless string with a very simple, not strange-shaped thing on the bottom called a bob. So, and the formula there is for the formula for a simple pendulum, but that formula doesn't describe anything that actually exists in the world, because if you dig into what that formula assumes, it assumes a massless string, which is pretty good. We have a pretty good assumption for a massless string, so that's why we're abstracting things. I don't want to use a rope here. I'm going to use something as close to a massless string as possible, which we have. And I want to use something down here that's theoretically a point mass, because that's what a definition of a simple pendulum is, a point mass at the bottom of a massless string, which of course, the two things that are impossible in the real world. We can't have something with no mass that's a string, and we can't have something that's a point, because a point has no mass also. The point where we would have this mass concentrated, as you can probably tell, we'll talk about more of this in the lab and in class later, is called the center of mass. And it's pretty easy without any calculations to see that the center of mass of a sphere is at the center of the sphere, which is why in our calculations we have to measure the length of the string and add the radius of the sphere to it to represent where the theoretical point mass would be that's at the end of this massless string that represents a simple pendulum. So we've come as close as we can in the real world to a simple pendulum. So we should get some results that are quite close to the simple pendulum values. The other aspect is that formula actually is an approximation. Should have a squiggly sign between the period and the length, because it's an approximation, and we'll talk about that much later, way late in the semester, where we talk about oscillatory motion, such as a pendulum. But to make that equation apply to our situation, we have to swing this pendulum through a very small angle. This is an angle of about 5 degrees one way and 5 degrees the other way. So that is the the most you want to swing it. The less the better. So don't swing it like this, because it no longer quite obeys that formula for a simple pendulum through periods of small oscillation. This is potentially a very accurate experiment within error within a couple 3/10 of the 1% if you're careful. In other words, 3 significant figures that we talked about last time. So we need to measure things very carefully, which means that my 1.004 meter stick is not good to use the end of it, okay, because you'd be 2 millimeters off. So what you need to do is somehow decide where to measure where the string leaves the clamp up here, and then measure down to either the top of the ball, the bob, and add the radius to it, or measure to where the meter stick is up against the ball next to it. So, but it makes it, excuse me, makes a big difference up here if you're off by a few millimeters. The last thing I need to remind you of, when I say measure periods for 3 very different lengths, I mean very different lengths. This length here is about 90 centimeters. That's fine. Closer to 100 centimeters would be better, not over 100 centimeters. And then the next length should be about 50 centimeters, which is like so. And the last length should be about 10 or 15 centimeters, which is like so. And of course, you can lower this instead of going up here. So, so the lengths should be very different, and the more very different they are, the better your results are going to come out, as it turns out. Okay, so 1 or 2 other things with regard to doing the experiment. You will, if you see the table that I give you, I suggest to you the table headings. There's a 25 periods column, which means count this swinging back and forth. That's 1 period, 25 times. And there's 2 lines there for you to do it twice. Now you say, well, why don't I just count 50 and do it once? Well, because if you miscount, you have a problem. A meter-long pendulum is what's often called a seconds pendulum, because it has a period of almost exactly 2 seconds. So if you're measuring the period of a simple pendulum that's a meter long, and you miscount by 1 period, you're going to be off by 2 seconds out of 25. And if you miscount by 1/2 period, in other words, you shut it off when it's going the wrong way, you only counted a 1/2 period at the end, and then you're going to be off by 1 second. So it's pretty obvious if you're off by 1 second or 2 seconds that you made a mistake. If you're off by 1/10 of a second, 2/10 of a second, 3/10 of a second, that's kind of human reaction time and observing when it actually has gone through a cycle and so forth. So that's not bad. So we do it twice, so you can look at those 2 numbers, and if they're not 1 or 2 or 3/10 of a second off for 25 periods, then you better just redo it and see which one really is right. Well, this is the last part of your measurements lab, and we've already done this, and we'll be talking in a little bit about graphing this and the graphing program. So this is my pendulum data table. I carefully did this experiment, and these are the results that I got, the data that I got. And so this is what's in your handout. That is the length in meters. It's always smart to convert everything to meters and kilograms and seconds before you start processing it, because that's the normal SI or MKS system. And so I'm going to do that, and I've done that here. So the length of the string in meters, then of course to get the ideal simple pendulum, you have to add the radius of the bob to it. And then I've also taken the square root in that process because of what we talked about earlier, and I'll remind you of that. And then measure 25 periods twice, and you'll notice these periods are all very close to each other. They're like about 0.1 seconds at the most off from each other, which to me means, which is why we did this 25 twice, that if you have a mistake in counting, you'll see it. For instance, if you look at the approximately 1 meter length, you see that a 1 meter length has, over here at the end, when I divide this number by 25, I get 2.010. A 1 meter pendulum, I think I mentioned that earlier, has it's called a seconds pendulum because it takes 2 seconds, almost exactly, to go, because this is almost exactly a meter, 2 seconds to go back and forth. That's 1 period. So it's a seconds pendulum, or a 2 seconds pendulum. In any case, these numbers are real close together. If it were off by 1 whole period, it would be off by 2 whole seconds. If it were off by half a period, where I started it this way and I stopped my stopwatch going the other way, which was wrong, that's a half a period, this would have been 1 second. So if it's 1 second off or 2 seconds off, using this as the best example because it's the longest length, you would get numbers here that were 1 or 2 seconds different, clearly telling you you've miscounted it. That's why we've done it 25 times twice, to not just get an average, but to make sure you haven't miscounted. Okay, so length, square root of length, plus radius in meters, both in meters, a period of 25 seconds, averaged, and then divide by 25 to get seconds. So we're going to plot then period versus length. Period is in the y direction, and length is in the x direction. And remember, the formula we're using is t equals 2 pi times the square root of the length divided by the acceleration due to gravity. I've rewritten this in a more, maybe a stranger mathematical form for reasons we'll talk about in a second. That is 2 pi over the square root of g times the length to the half power. If I compare that to the slope-intercept form of a straight line, which we want to force it to be a straight line, we talked about that earlier, just for ease of comparison's sake, I see that the slope, x, of course, is the square root of the length. That is the length plus the radius, as we know. So I should have written that L plus square root of L plus R there, but you know what I mean. This is the ideal simple pendulum length. X is the square root of the ideal simple pendulum length, and M is the slope of this curve, and B is the y-intercept. And of course, a zero-length pendulum will have a zero-intercept. So you can check your data by looking at how close your y-intercept, your time-intercept is zero. A zero-length pendulum would have a zero period, of course. So if you're off a little bit, like 0.001 or something seconds, that's because it's data. So this says that the slope is 2 pi over the square root of g. Again, if g is in meters per second squared, you get one number, and if you left g in centimeters per second squared, and you take the square root of it, you're going to get a number that's 10 times different. So convert everything as soon as possible to kilograms and meters and seconds, and you'll be in good shape. So here's the graph we're going to look at in a minute with these data. Your 3 data points, your small, medium, length, large length, and plotted versus the square root of the length plus the radius of the simple pendulum. So let's go over and take a look at the program, and we'll see what that looks like on graphical analysis. So here's the graphical analysis program, 3.8.4. You should have that in your file. And let's just click on that and see what happens. That brings up a blank graph, and you just put your x and y values in, and our x and y values are as follows. The first x is 0.717, and the first y is 1.445 seconds. The second L value is 1.0025, and the corresponding time was 2.010 seconds, and the third value is 0.432. That's the square root R plus L in meters, square root of meters, and the corresponding period was 0.812 seconds. Okay, so there are 3 data points, and if we go over here to the second icon from the right and park on it, we'll see that it says linear fit, which is what we want. We've sort of linearized this normally quadratic relationship that is period versus the square root of the length by plotting the square root of the length, so it turns out to be a nice straight line. And there's our straight line down here, but it's kind of in the corner of the graph, so let me go over to the blue A button here, which is the auto scale button. Okay, so here are 3 data points. Again, you see the point predictors around them, and that's just let us tell where the points are if they happen to miraculously fit on the theoretical straight line. And let's go over to the auto scale button here, and that's already scaled. And so the R value here is the linear fit button, the second one from the right. And if we draw the straight line through those, you see that the points don't quite fit the line. That's typical data. That's not perfect. And so we have a very close fit to the line. And if we want to find out the error in that slope, for instance, or the error in the intercept, whichever, if you double click on that box, we'll get another box that has some options here, which changes the number of significant figures or decimal points and so forth. What we really want is the show uncertainty option, which gives us, hit the OK button, gives us very nicely the error in the slope, which is what we're looking for, because the slope has got G in it, which is what we're looking for, and the error in the intercept. So the intercept, even including the error distance, is 0.08 roughly, and the error is plus or minus 0.05. So the slope doesn't exactly, or the intercept doesn't exactly hit 0 within its bounds. But again, this is data, and it comes very close. The slope is what we're looking for, and the slope value is 2.093 plus or minus 0.065. So it's 0.209 plus or minus 0.065. Okay, 2.09 plus or minus 0.07 to be consistent in the 2 values to the hundredths place. So 2.09 plus or minus 0.07. And you want to compare that to the value that you get by plugging 2 pi over the square root of G, which is 9.8 meters per second squared. That number comes out to be something like 2.07, if I remember right. And if that's the case, our error range includes the expected value, 2.09 plus or minus 0.07. So that's pretty close data, and this result should come out fairly close, because it's a pretty simple experiment. We have essentially a simple pendulum here as best we can create it in the real world, and you want to print that out. So I would recommend that you go to the file routine here. Well, first of all, we should label this. Okay, if you double click on the x-axis, which is the length axis, we can put in here the name, such as, it's not the length, it's the square root of the length, so SQ dot RT length. Okay, and then we can put the units in, square root of meters, and that's done. So there it appears down there. And then do the same thing for the y direction, and the y direction is period, and that's in seconds. And that takes care of the y direction, so it's labeled over here nicely. And if you want to label the entire graph, such as pendulum versus length. We can double-click any place on the graph, and that will bring up the title box, so we can put length versus, oh no, wait, sorry, I don't want to put length versus, I'm going to put period versus square root of length. Of a pendulum, or whatever title you want to give it, and then hit the done button. And we have a very nice graph with the error built into it, a nice straight line, best fitting the data points, thanks to the computer's analysis, and labeled. Couldn't ask for anything more. So we go over to the file option, and there's two print options. There's a print option which will print this whole screen, which you really don't want because you've got your data already in your data table, so you get a much bigger graph by going down here to print graph only, basically, and then hit the OK button, and wait a little while, and it should print out for you. So that's it.